Alright guys, so here's part 2 of section 1.2 exponents and radicals. Today we're going to specifically be focusing on radicals. Alright, so this is on the first page of your notes, so if you'll go back and fill out this last box for parts of a root, and basically we're used to seeing this all the time, but the number inside of this radical is called the radicand, and the small little number on the outside is called the index. Now most of the time if we don't see a index number, we're just going to assume it's 2, and that's where we call something the square root. If the index is 3, then it's called the cube root. After that we don't really have names, it's just the 4th root, 5th root, etc. Alright, so principal roots. The idea of principal roots, these are the things that you think of most of the time when we just say find the square root. So the square root of 16 is equal to 4 because our opposite operations here work. Because 4 squared is equal to 16, if you go backwards, then the square root of 16 is 4. Now this works for other indices. So for example, I'm looking for the third root of negative 8. So basically I'm trying to think of a number raised to the third power because the index is 3. And then I get negative 8. So that means negative 2 to the third power, that's going to give us negative 8. So then that's what that expression is equal to. Some of these properties are going to look similar. So this first one is really the one we're going to focus, the first and second one are the two we're going to focus on. So when you take, for example, the square root of a number squared, those are sort of opposite operations. Now, the second line here also works as long as a is greater than 0. Obviously, on that first one, if a is less than 0, then we have to watch out because sometimes we'll get imaginary numbers, but if the index is odd, then we still might be able to simplify that. Some laws that work. So for this one, when you have a product inside of the, or a product as the radicand, basically we're going to try to break down factors by the nth roots, and we're going to do that quite a bit here in a minute. Down here with our quotients, basically the root can just get applied to both the numerator and the denominator. Now some things that are not laws. Okay, this is very important that you notice on your notes it says these are not laws. Unfortunately, we can't just break things down and, you know, we have the square root and both these are squared, but it doesn't work to just kind of get rid of them because of the operation there. Same thing. Because this has a plus or a minus sign inside of this, we can't really break anything down. We can only break things down as these top two examples when this is multiplication and then this one is division. All right, so to simplify radicals, a couple of things that we are going to focus on. First, we're going to break down the radical by perfect n roots. And again, n stands for the index. Then, I think of this as a recess. So remember back to elementary recess. The good numbers get to go outside. And in this case, the good numbers are the perfect squares or perfect cubes or perfect whatever in terms of our n, our index. The bad numbers stay inside as the radicand. Now, variables are actually really easy on these. We're going to take our variables, we're going to take our exponents in groups of n. Okay, and then those are going to go outside. So then any leftovers stay inside. So now we're going to look at a couple of examples, and I think that that'll sort of make sense with these steps. So the first example, example 3a, is the square root of 50. So again, this is a number, So we're going to try to break down the radical by finding perfect square roots. Because that index is 2, we're going to look for perfect square roots. Now obviously the bigger number, the quicker this problem is going to go. So I need to find perfect square roots that are multiples, or that are factors of 50. And the easiest one to think of are 25 times 2. Now 25 is my good number, so when I take the square root of 25, this is what we have to be really careful with. There's kind of like these magical doors that the square root of 25 goes out these magical doors, and through those magical doors it becomes 5 on the outside. Now 2 is not a perfect square, and so that's why that number is going to stay inside. Example 3b. Here's our index, so now we're looking for perfect cube roots. Now this one's a little bit tougher because 320 is a pretty big number. But I'm going to start off with some small ones because I know these smaller numbers pretty easily. 8 times 40, that gives us 320. And 8 is a perfect cube because 2 times 2 times 2 gives us 8. Now, I also then noticed that 40 can be broken down into 8 and 5 again, which makes this problem a little bit easier. Now I've got these 2 sets of perfect cubes. Now remember, there's these magical doors, so when 8 goes through the magical doors, this becomes a 2, and then this becomes a 2. Now this is just one gigantic multiplication problem. So I have 2 times that radical. And the stuff on the inside, you still need to, the stuff on the outside, you still need to multiply. So then there is your final answer. All right, this time we've got some variables thrown in here. First, we've got to find that our index is 3. Now, 16, we know that we can break that down into 8 and 2. So I'm going to actually sort of work on my answer all the way down here. Now, we start looking at our variables. So from these exponents, I'm going to take them in groups of 3. Okay, the index tells me that I've got to take groups of 3. Once I get a group of 3, then it goes through the magical door, and then just one of it ends up on the outside. So I'm going to start with the x's. Obviously, the exponent is 3, so that means I can make one group of 3. So I'm going to take x to the first outside once it goes through those magical doors. Now, for 8, right, I can break down 8 to be a group of 3, and then we're left with 2. So here we have 2 groups that get to go outside, so that's going to be y squared. There's still 2 leftovers, so you still end up with a y squared on the inside. For the z, I'm going to look at 4, and I'm going to take it, I'm trying to find groups of 3, so I can find one group of 3 for the z, and then there's also 1 left over. Now, one thing to be really careful with, right here, this z and this z, those are not the same things, right? Because one of them is outside of the radical sign, while one of them is still, we're still taking the cube root of it. All right, another example that sort of combines the stuff we've been working on. This just asks us to multiply things first and then break down our problem. So I'm going to multiply and get 18, and then this is just going to be a to the 7th and b to the 3rd. Now this works from that part 1 because we're multiplying a squared times a to the 5th. That tells us to just add the exponents. Now I'm looking for perfect square factors that give us 18. So the 3 gets to go outside. Remember, this index is 2. So for a to the 7th, I'm looking for groups of 2. So when I break down 7, there's a group of 2, there's a group of 2, there's a group of 2, and 1's left over. So you'll notice I was able to take 3 groups outside, which means we get a to the 3rd on the outside. For the b, I have b to the, actually there's a typo here. Let's change, on your notes, this is a 3. I apologize for that, guys. So now this gives us b to the 4th here. And now when I'm taking out groups of 4, I get 2 groups of 4, or 2 groups of 2. Now we do still have that a that was stuck on the inside. And we have the 2 from the whole number, or from the real number. So then that is your final answer. All right, the next thing is called rationalizing a denominator. Now this kind of puts together a couple of these different topics. So the big thing with rationalizing a denominator, we need to match up or to get the n index. So in our denominator, we need to, basically we're going to use that first property that told us, when you square a square root, basically the radical disappears and you're just left with the whole number. That's what we're trying to do here. So for this example, I know my index is 2. So that tells me that I need 5 squared. I want to be able to take the square root of 5 squared because I know that's 5. But right now, I only have the square root of 5 on the bottom. So to get an extra one, all I'm going to do is multiply by the square root of 5 on the bottom. Now I have the square root of 5 times the square root of 5. But if you multiply on the bottom, we need to still multiply by the same thing on the top. And so now this is the square root of 5. Down here, this is the square root of 5 squared. I don't necessarily need to see this step in the future because the whole idea of rationalizing the denominator, we're trying to get that bottom part to disappear kind of without doing the extra work. So in the future, this is not necessary. But for right now, I just wanted to kind of write it out so that you see what we're actually doing. All right, this next one. First thing we look for is we find an index of 3. So now that means I only have x to the first on the bottom, so I need x squared. That's going to help me have enough exponents, enough variables on the bottom to get rid of the radical. Whatever you do on the bottom, you have to do on the top. And so now on the top, we have the cube root of x squared. Now on the bottom, all that stuff took care of each other, and we don't have a radical anymore. We're going to skip example 4c. We'll come back to that eventually. A couple other things with rational exponents. Rational exponents are exactly what they sound like. This just means there's a fraction in the exponent. Okay, there's a couple ways that we need to be able to rewrite these. And you're going to see how this is helpful. Different people do these problems a little bit different ways. So if you've done this a certain way in a previous class, absolutely keep doing that. If you don't necessarily have a system, here's what I'm going to encourage you to do. We're going to rewrite the base as a power to the denominator. And then second, we're going to use our exponent rules to simplify. Now this first step doesn't sound great in English, but I think once you start to see it, I think it's going to make more sense. So for example 5a, obviously we have these rational exponents, which your calculator can actually take care of. So that's a good way to check your answer. But when you need to show your work, we want to rewrite it a little bit different. And then once we get to variables, obviously you can't use your calculator for that. So if you look back at your notes, it says rewrite the base. So the base is negative 27 as a power. So I need something as a power to the denominator. So if I look up here, there's the denominator. I need something to the third power. So then you just kind of hope it's one of those smaller numbers. And we know that. So we know that negative 3 to the third power is equal to negative 27. Now we're going to do the same thing. 4 is our base. We need something. Here's our denominator, something squared. Okay, this one's pretty easy. we know that 2 squared gives us 4. Now we're going to go ahead and rewrite these in their places. So I'm going to change negative 27 to negative 3 to the third. Now it's still being raised to the 2/3. And I'm going to replace 4 with 2 squared, and it's being raised to the negative 5 halves. Now, the way that you can check this, remember this is really just using the power rule. So with our power rule, we know that we're going to multiply the exponents. So right here, 3, remember that's really 3 over 1 times 2/3. Those 3's cancel out, and now we have a whole number. So now we're done with fractions, which is what we all want to have happen. We want to get rid of those fractions when we can. So now this guy is just negative 3 squared. Over here, 2 times negative 5 halves is just 2 to the negative 5th. Now, an easy way to check this, if you ever get to this next step and you still have fractions as your exponents, you know that you have done something wrong. Now we're going to simplify just like normal. This should be a review. We have 9, but then actually we're going to change that because I see this negative exponent, so the 9 is going to stay on the top, but we know 2 to the 5th is going to go on the bottom, and that's going to give us 32. So then there's the answer for that problem. Let's do one with variables real quick because this is the type of thing that you can't necessarily do on your calculator. So this one will be r to the 2/3, and then this one would be s to the 6/3. Now r to the 2/3, we can't really do a whole lot. We can't rewrite r as anything different. So then what we're actually going to do is we're going to use one of those properties and we're going to change that into a radical. Now s, you'll notice that 6 over 3 is just equal to 2. So this is s squared. And then this r, we're going to change to be a radical. Now, it's the same value, but it's just a little bit nicer way to write this problem. Example 5C, we will actually do that one together another time.